welcome back. So now I'm going to make use of Wolff's equation expression to get a Van Laar equation out of it. Okay. So Van Laar is a special case of Wolff. So special case of Wolff. It's used for mixtures having molecules which are chemically similar but different sizes. Some examples are benzene and isooctane, the same example which we've been trying to use. Okay. So if you look at let's say if it is 1 and if it is 2, its molar volume is 89 cubic centimeter per mole, whereas here is 166 cubic centimeter per mole, okay, at 25 degrees Celsius, clearly suggesting that these are of different sizes. Now, if you ignore a higher order term in Wolff's expression, if you consider just the first expression, right, and this expression, if you consider, you are going to get the Van Laar equation. So, if you remember this, Zi is equal to Xi Qi divided by X1 Q1 plus X2 Q2. So, let me get there and write it here. So, what I am trying to say is the following: Gx by RT X1 Q1 plus X2 Q2. If I consider only the first term, right. So, this is nothing but Van Laar. Now, you can plug in Z here. So, this can be written as 2 this one, and this is X1 Q1 divided by X1 Q1 plus X2 Q2. This is square and this would be multiplied by X2 Q2. Okay. So, now you can simplify this expression. You should be getting Gx, if I take this part the other side, okay, then I get RT, and this is going to be 2A12 X1 X2 Q1 Q2 divided by X1 Q1 plus X2 Q2. Okay. Now, remember that we are a little bit comfortable with A's and B's, because the reason is that that makes equation simpler, and start from this one constant Margolus equation. So, we can actually write it in that form. If you do the calculations, you know that from the fact that the activity is related to the partial gives excess property, and so that means you should be able to get this expression similar to how we got the one constant Margolus equation and obtained the activity coefficient. Okay. So, if you do that, so I am not deriving it, I get the following expression: A bar 1 plus A B x1 by x2 2, and ln gamma 2 is B dash 1 plus B dash by A dash x2 by x1 2, where A dash is 2q1 A12. Remember that A we referred earlier also as interaction parameter. So, indeed, if you consider A12 is an interaction energy, and Q, what was Q? Yeah, so basically the Q is basically the volume, effective volume of the molecule. So, not the volume ratio, whereas Z is a volume ratio. Okay. So, A dash is 2 Q1 A12, whereas B dash is 2 Q2 A12. Now, we need to use some kind of experimental data to obtain A dash or B dash. Usually dilute solution informations are available from the experimental data. So, if you use that information from the experimental data, then A dash by B dash, okay, is nothing but Q1 by Q2, okay. And what is A dash? How do you get the A dash here? So, if you consider, let us say in dilute solution x1 goes to 0, then this will be simply ln gamma 1 infinity is nothing but A dash. Similarly, ln gamma 2 infinity where x2 goes to 0 will be B dash. So, A dash by B dash ratio, which is q1 by q2, okay, is nothing but ln gamma 1 infinity by ln gamma 2 infinity. So, this is relation you can obtain from the experiment. So, there is a relation between these constants, okay, which is related to the infinite dilution activity coefficient. Okay, so often we use the above relation in this form. Or we use in this form. Okay, this is nothing but a two constant or two parameter expression or two parameter theory, we say that. Okay. So, this is a Van Laer expression. You can easily make use of this for benzene isooctane as well as N-propanol and water. It works very well. Okay, so it captures the complexity of that nature of dissimilacing. Remember that for N-propol and water, it is basically hydrogen bond is also playing a role. Now, this expression I can rewrite actually. Let me just further. Now, though the derivation of Van Laer suggests that it is good for solution of relatively simple system, preferably non-polar, but it is also used outside this assumption. So, it is used for polar also. Okay, that is what I said, N-propanol and water system. Okay. So, it is capable of reproducing data for complex mixtures. So, let me rewrite this expression, rewrite this here in this form x1 x2, I now write in this form. Okay, x1 x2 divided by GE, this can be written as x1 A dash by B dash plus x2 1 by A dash RT. Okay, or I can write this as 1 plus A dash by B dash minus 1 by A dash RT. Okay. So, what this suggests that x1 x2 by GE or GX, it is the same thing, same nomenclature in this course, versus x1. This versus x1 is a straight line, and this expression, this if you have the data available, this can be used to obtain A dash and B dash, right. This is what it tells you. If you have the data of this composition and G axis, okay, you can plug it and obtain the A dash and B dash out of it. Okay. Now, usually A dash and B dash are insensitive to pressure, but not to temperature, okay, because it depends on the temperature. But if it is insensitive to temperature, then this will be a athermal solution. Okay. Now, practically A and B are often assumed to be independent temperature if the temperature range is not too great. Okay, this is a practical consideration. Now, often you may have A and B known at specific temperature. So, and then you would like to find at different temperature. Okay. So, it is customary to write at constant x ln gamma I is C plus dt. So, you have the information, you can get it at different temperature, but using this kind of customary expressions, okay, where C and D are empirically determined. Okay. So, usually when you see this kind of expression, and if C is equal to 0, this also indicates the solution is regular. Now, this is something which I am going to spend last few lectures on it. Solution is regular, which essentially means S excess entropy is 0. If D is equal to 0, that means it is independent of temperature, then solution is athermal. Which means Hx is 0. Okay, this is something which we can save by looking at it if you are aware of all the derivations, but I will just assert it now and we will look at it in the later part of this course, that was the last few lectures. Okay, so now that we have expressed very well the Van-Laer equations, the other set of equations are also available which can be derived from the again the Wolff's expressions. So, if you consider molecular sizes to be equal, which means Q1 is equal to Q2, okay. This essentially means that x1 Q1 plus x2 Q2 is nothing but Q, which essentially means Zi is equal to Xi. Okay, if you go to the definition of the Zi will be nothing but Xi. Okay. In that case, I can consider the expression of the Wolff's expression in this form. Okay. So, this will continue. This should have been say x1 x2 here, I think, yeah, so 2 terms, right. Okay, fine, x2 and then this higher order terms of x1 and x2, right. You can come up with this expression particularly containing only till x2 or till 4th order of composition this. So, again I am skipping all the derivation and you do not need to remember, the most important thing is that how it is derived or could be important, as well as the philosophy of these expressions is actually, I feel, that more important rather than remembering these expressions. Okay. So, this is the expression which comes up for Allen for binary mixtures having the molecular sizes are constant. From here, okay, we should be able to connect or get this something is this Margulies equation of 2 constant and 3 constant. For 2 constant, C dash is equal to 0, okay. For 3 constants, C dash is not equal to 0, okay. Where A's and B's are connected to nothing but, for example, A dash is nothing but Q 2A12 plus 6A112 and so forth. Similarly, B dash is Q 6A112 minus 6A122 and so forth. So, as once you derive, you should be able to find all these things. So, this Margulies equation for 2 constant and 3 constants has a basis of molecular sizes to be equal, okay, and it is derived from the Wolff's equations, okay. So, in practice you can see that this 2 constant and 3 constant Margulies equation should not be used for the system having dissimilar sizes, but in practice they are also used, okay. So, last equation or the expression is due to Scott-Hart, which I am going to talk in this, and then I will stop and focus on some examples. So, this is a expression where the Wolff's expression is truncated at the 3rd term, okay, and we put the ratio of this sizes as simply this. As I said, this is one model. Remember that earlier I said that one model is this. This is nothing but a Scott-Hammer equation, and here if you use this expression, then the following expression of activity coefficient comes into. So, this is again I am writing this without deriving it. Okay, where A dash and B dash are functions of you know there's A's and B's. So I won't write it in detail because I don't expect you to remember this as well. But what is important is that Scatchard hammer captures the complexity in between Van Laer and Margulis. Okay, so intermediate in complexity. Okay, so we may use some of this expression to do some kind of examples. That's a different matter, but the idea is that this is another possibility if you have intermediate in complexity. Now, what is the intermediate in complexity? Where of course the size differences are there. That is something which is part of this the complexity. Now, in addition to this, we can also discuss various different expressions which has some sound basis. Wilson, NRTL, which is a non-random two liquid local composition, and UNIQUAC, which is universal quasi-chemical theory. Okay, so this is something which I won't go into details, but one can get an expression of the activity with respect to different variables. Okay, so at this point I will stop here and I will I will work on some examples in the next lecture. Okay, so see you in the next lecture.